Welcome, scholars, to second year physics, the Cosmology unit. What is cosmology? Cosmology is the branch of science that seeks to understand the origin, the evolution, the structure, and the ultimate fate of the whole universe, as well as the natural laws that keep it in order. Modern cosmology is dominated by the Big Bang theory, which brings together observational astronomy and particle physics. One of the first concepts we meet in the cosmology course is time. We're only aware of the passage of time when we observe something changing. For example, the hands of a moving clock. We see the hands move, so we know time is passing. That brings us to the idea of the arrow of time. This is a very simple idea. It simply tells us that we always move from the past forwards into the future. That's the arrow of time. Time always moves from the past to the future, but never the reverse. A slightly trickier idea is entropy. It's a complicated sounding word, and it often causes confusion, even to older pupils. Well, we're going to have a very simple definition of entropy. For us, entropy is... Here's a good example. Look at these two pictures. They're of a tidy bedroom and a messy bedroom. You might want to consider which one yours is. Well, here's a question. Which bedroom is ordered and which is disordered? If you've not answered this question before, pause the slideshow just now, consider your answer before proceeding. And there's a second question after this as well. Well, the answer is that bedroom B is clearly very tidy, that's the ordered one, and bedroom A is very messy, that's the disordered one. Question 2. Which bedroom has high entropy and which one's got low entropy? Well, before answering, remember, entropy is a measure of disorder. So, the messy bedroom is going to have the high entropy, so that's bedroom A. Bedroom A has the high entropy, and bedroom B has the low entropy, because it's very tidy. We now consider a sort of cosmic timeline going from the Big Bang, right at the beginning of the universe, and ending up at the present day. So I'm just going to take you through the steps that occurred, the important steps. Well, the Big Bang, we were going to say, occurs at stage 1, right at the very beginning, so no time has elapsed yet, and modern physics really doesn't understand very much about the Big Bang. Between 0 and then 10 to the minus 43 of a second, that's 0.42 zeros and then 1 seconds, an incredibly small amount of time. During this very, very brief instant, no matter yet existed. It was just pure energy. This is called the Planck time, and that's a very, very small number, 43 places after the point. After about a millionth of a second, that's 10 to the minus 6 seconds, the very first particles of matter were formed, and these are called quarks, and we'll hear more about them later on. After about a second, the universe had cooled down enough actually, so that the first sort of larger particles, protons and neutrons, began to form. Between 1 and 10 seconds, the cooling continued, and the universe cooled down so much that electrons began to form. Now, we say cool, but still incredibly hot by our standards. These electrons, of course, are exactly the same electrons that you have experimented on in your electricity course, the same electrons that flow along wires and come out of batteries. Then at about 10 seconds, something dramatic happens. This is the point at which light first appears. Previously, everything was dark. So for the first 10 seconds, there was just complete darkness. Light came, elementary particles came, but no light yet. 3 to 20 minutes. Cooling continues, the temperature keeps falling, and eventually hydrogen becomes made and turns into helium by nuclear fusion. After 150 million years, stars begin to form. So it took a huge amount of time, 150 million years before the first stars begin. After about 500 million years, the stars have clumped into galaxies. They've begun to form. After 8 billion years, the solar system forms. After 9 billion years, we believe the Earth formed. And then today, 13.7, 13.8 billion years later, we are at today's point in time. And as we'll see later, the galaxies are all flying apart, receding from us at this point. So, the age of the universe, we believe, is about 13.7 billion years old. We use scientific notation to write numbers like this, and that's an important part of this course. In order to handle scientific notation, you need to be able to use your calculator in scientific mode. So whenever you're using it in physics, set it up to be in scientific mode, and here is how you do it. Shift then setup, that gets you into the setup zone. When you're in there, select option number 7, SCI for scientific notation. Then press 3. That basically tells the calculator to use 3 digits in the scientific notation, which is enough in S2. And you're ready now to use your calculator in scientific notation. In physics, always use it in this way. In other subjects, you might need to return to normal notation. So to do this, press Shift and then Set Up again into the setup zone. Then press option 8 for normal. That tells the calculator not to use scientific notation. And then press 1 and you're now back in the normal mode. Check with your teacher about which mode to use in other subjects. Okay, let's do an example involving scientific notation. We want to write the number 100 in scientific notation. Now 100 is just 10 times 10. Now notice that we have multiplied 10 together 2 times. So to summarize that in scientific notation, we write the number 100 as 10 to the power 2, or you can say 10 squared. Very often in scientific notation, we might write 1 times 10 to the power 2, just to show that the only number multiplying onto the 10 to the 2 is a number 1, but it just means exactly the same as 10 to the power 2. So, in scientific notation, 1 times 10 to the power 2 means exactly the same thing as the number 100 in normal notation. Now the actual buttons you press on your calculator to enter this in are as follows. So practice doing this right now if you've not done this before. Type in the number 1 on your calculator, then the button that has times 10 to the power x on it is down in the lower section of your calculator keypad, then the number 2, and then equals, and your display should read 1.00 times 10 to the 2. An interesting experiment we do in this course is measuring the speed of light. And the experimental setup to do this is shown on your screen now. So if you look at it, we have a light transmitter. So if you could identify the light transmitter. It sends out a beam of light. That's called the incident beam. That beam travels a length L, usually several meters, reflects off a mirror, bounces back, so we've now got the reflected beam. The reflected beam comes back to a receiver and is received and detected. And both the transmitter and the receiver are both connected up to a device called an oscilloscope, which basically tells us when the light pulse leaves and when it returns and how long it took to do that. On the screen of the oscilloscope, you'll typically get an image like this. Now the tall peak is quite tall. That's measuring the incident pulse leaving. And on the y-axis, it's basically the brightness of the light, the intensity of the light. So the tall pulse means a bright light. Now a little while later, because on the x-axis is time, a little while later the reflected pulse returns, and it's much smaller because the returning beam is weaker. It's lost energy during the journey and during the reflections. Now on the oscilloscope, we identify the middle of the incident peak, shown by the red line there. We do the same for the return peak, and the time interval between them is the time for the light to leave the transmitter and return to the receiver. So that's the round trip time. Now when we do this experiment, we repeat it several times and we get results something like this. So for a round trip distance of 8 meters, that's 4 meters to the mirror and 4 meters back, you can see the sorts of time we get. They're all round about 2.6 times 10 to the minus 8 seconds. The reason we need the special oscilloscope, incidentally, is to measure these tiny little times down to 10 to the minus 8 seconds. Requires a very accurate oscilloscope. Now in the third column, we're basically going to use the speed equals distance over time equation, and we'll divide our distance, which is always 8 meters, that's the round trip distance, by the time taken. We did 5 repeats of the experiment here. You get slightly different times on each occasion, simply because of experimental error. So when we work out the speed, for run number 1, we get 3.07 times 10 to the 8 meters per second. There's run number 2, run number 3, run number 4, and run number 5. So they're all quite close to about 3 times 10 to the 8 meters per second. Now when we do an average then of all of this, you can see that the distance between transmitter and mirror, we'll call that L, length L, is 4 meters. So the round trip time is 8 meters. 8 meters. The average travel time for the whole trip, when you add up those 5 times and divide by 5, you get 2.60 times 10 to the minus 8. And the average speed of light, approximately, is 3 times 10 to the 8 meters per second. So we have actually measured the speed of light. This is a very important number in nature, and you should memorize it. So the speed of light in air, strictly speaking, it's actually in a vacuum where there's no air at all, but we measured it in air, is 3 times 10 to the 8. Now we'll write that as c. C is the special symbol given to the speed of light, and it's 3.00 times 10 to the 8 meters per second. What's interesting is this is actually the greatest speed that is ever achievable in the universe. You cannot get a speed any greater than the speed of light. It's also the speed of all electromagnetic radiation, things like ultraviolet, infrared, radio waves, etc. No body which has mass can ever travel at the speed of light. We can get very light particles like electrons to go quite close, but we can never actually get to the speed of light if you have a massive particle. I feel a worked example coming on, so let's do one now. As before, if you've not done this worked example before, pause the slideshow and calculate the answer first. If you have done it before, you can treat this as revision. So we wanted to work out then how far away is the moon if light takes 1.28 seconds to travel from the moon to the Earth. Well, we list our variables. The speed is 3 times 10 to the 8. You're supposed to know that. The distance is the unknown, and the time is 1.28 seconds. So we've listed our variables, and we now state our equation. Speed is distance over time. Put in our variables. D is the unknown. Now we need to rearrange that for D, so the 1.28 comes round under the equal sign and multiplies on, and we get this. And when we calculate the answer, the distance is 3.84 times 10 to the 8 meters. That's the distance to the moon. It's about 250,000 miles. We now come to the light year. What is a light year? A light year is the distance travelled by light in 1 year. It's a unit of distance. So let's be absolutely clear here. The light year is not a measure of time. A year is a measure of time, but a light year is a measure of distance. Let's try an example. Again, if you've not done this before, pause the show and try the question first. There's a star called Proxima Centauri, and it's 4.2 light years from Earth. If light leaves Proxima Centauri on the 1st of January 2016, when, to the nearest year, will we see it on Earth? Here's the best way of setting this out. We've got 3 key points in our solution: when the light leaves the star, how long it takes, and when it arrives on Earth. So set up a little grid like that. You don't need to draw the lines, but just put the headings. It leaves in 2016. We're told that in the question. What's its travel time? Well, it's 4.2 light years, but in our problems we're just going to round up to the nearest whole year, so we'll call it 4 years. So that means 2016 plus 4 years, it's going to arrive sometime in 2020. So light from Proxima Centauri will leave in 2016, but it will arrive on Earth in 2020. Looking back in time. In the problem we did earlier, the observer on Earth in 2020 was seeing light that left the star Alpha Centauri 4.2 years ago. He's only now just seeing it, but it left 4.2 years ago. So he is actually quite literally looking back in time. There's the light travelling for 4.2 years before it reaches us. And this is true of every single star we see in the sky. Even the sun. Light from the sun actually takes about 8.5 minutes to reach us on Earth. So when we see the sun, we see it as it was 8.5 minutes ago. Hubble's Law. Sir Edwin Hubble made some really quite profound discoveries in the 1920s about what the galaxies were doing. And if you look at this graph, it's a similar graph to the one that Hubble himself plotted based on his observations. So what he saw was that if you plot the distance to a galaxy, we'll call it d, in millions of light years, very, very big distances on the x-axis, then you plot the speed the galaxy is moving away from you on the y-axis. That's called the recessional speed. You get a nice straight line. Well, the first thing to note is that Hubble discovered all the galaxies were moving away from us. Quite an astonishing surprise, really, for physicists at the time. But he actually discovered something even more remarkable, and that's shown in the graph. Because if you look at the graph, the further away the galaxy is, the bigger the distance to it, that's to the right of the x-axis, the faster it's moving away from us, the greater the recessional speed. And this has led to what we call Hubble's Law. Hubble's law, in a simple expression, basically says the further away a galaxy is, the greater its recessional speed. That's its speed moving away from us. And in fact, all galaxies are moving away from us, and they're all moving away from each other. Now, if all the galaxies are moving away from us and from each other, the only conclusion we can make is that the universe itself is expanding, and that's what we believe to be the case today. Here is a little simulation. Now, in this diagram, we've got the Earth in the middle, and we've got some galaxies around it. Now, we should really point out this diagram is nowhere near to scale. The galaxies are full of billions and billions of stars, and they're considerably larger than the Earth, and they're considerably further away than shown here. But this will give you the general idea. So, if you look at this slide, you'll see the galaxies are in a certain position. A bit later on in time, they're further away. If we wait a bit further, they're even further away. They're constantly moving away from where they began. And eventually, they're very far away. So the galaxies are getting further apart as time goes on. The universe is definitely expanding. Cosmologists, when they discovered Hubble's ideas, thought to themselves, okay, if all galaxies are moving further away from each other, let's imagine that we were going back in time. That must mean that if we go back in time, the galaxies would then get closer together again. So they imagine going back further and further and further in time, the galaxies get closer and closer and closer together, and thought, well, hang on, at some point in the past, all of the galaxies, that's all the matter that existed, must have come to the same point, because they all seem to be emerging from a single point and expanding from a point. So they've all gone back in time to the same point in the imagination of the astronomers, and so we call this the Big Bang. The Big Bang, well, the Big Bang at the centre is at the centre of the expansion of the whole universe. It occurred around 13.8 billion years ago. We used to consider it to be 13.7 billion, but the more recent figures suggest 13.8. It was an unimaginably huge explosion of energy from what we consider to be an infinitely small point. So everything in the universe, all the matter and energy, came from this tiny, tiny point. And we really don't understand how this happened. However, what we do know is that as all the energy radiated outwards in the early universe, it cooled down. And as you saw in our timeline earlier, particles of matter began to form fairly quickly. And as you saw also, the very first particles were things called quarks. Quarks began to form about a millionth of a second after the Big Bang. And these particles, given the name quarks by physicists somewhat humorously, really an invented word, are the smallest particles of matter we have yet discovered. And all of our experiments show there are 6 different types. There's the up quark, and its symbol is U. The down quark, symbol D. The strange quark, symbol S. The charming quark, symbol C. The top quark, symbol T. And the bottom quark, symbol B. Protons and neutrons. As the expansion of the universe continued, it cooled further. And after about a second, as you saw, protons and neutrons began to form out of the quarks that were already there. So we now know that protons and neutrons are made of quarks. It takes 3 quarks to make a proton or a neutron, and protons and neutrons make up the nucleus, that's the very core of all atoms. Now the quarks inside the proton or the neutron are held together by really quite incredibly strong forces, which we call gluons, and yes, they are named after glue. Physicists do have a sense of humour. Here is the structure of a proton. The proton has got 3 quarks, 2 ups and a down. Always 2 ups and a down in a proton. So a proton is basically an up-up-down combination of quarks. Look at the neutron. Can you spot the difference between the neutron and the proton? Well, the neutron still has 3 quarks, but it has up, down, down. It's got a different combination. So the neutron is up, down, down. The proton is up, up, down. Electrons. Further cooling took place as the universe expanded between 1 and 10 seconds, allowing electrons to form. These electrons are the very same as the ones flowing along wires in your electricity experiments. And of course, as you know, electrons have a single negative charge. Light. At around 10 seconds after the Big Bang, light first appeared. Until then, it had been completely dark. Light is pure energy, unlike other particles, I should say. It has no mass, pure energy. Here then is a summary of the evolution of the universe. You have all of this from earlier slides, so you can pause if you need to study any aspect of this, and you're not expected to memorize the table. The first nuclei, formed between 3 and 20 minutes, had no electrons on the outside. If you look at the diagram, you can see that the first particles that formed after the quarks were protons and neutrons. And if you look at the proton there, that's actually a hydrogen nucleus. A single proton on its own, with no electron going around the outside yet, is basically a hydrogen nucleus. So those were the very first nuclei formed, hydrogen nuclei. And because they were basically just protons, they had a 1+ charge, because that's what protons have. Later on, the first atoms formed. So the universe kept cooling, and it cooled enough so that the electrons, which had previously been flying around at tremendous speeds, slowed down a bit, enough to be captured by these protons. And so the electrons started orbiting, captured by the protons. And once you've got an electron orbiting the proton, you've actually got an atom, not just a nucleus, but an atom. And that's an atom of hydrogen. So that's 1 proton and 1 electron orbiting the nucleus. So hydrogen is the first element. These are the elements that you will have perhaps seen in chemistry in the periodic table. And an element is a substance that consists of only one type of atom. So, for example, in hydrogen, all the atoms are hydrogen. So hydrogen is an element. So hydrogen is the first element. It's the simplest element, and it's the very first element in the periodic table as well. Gradually, as time went on, other elements formed. After about 150 million years, hydrogen atoms began to gather together through gravitational attraction. Basically, each hydrogen atom attracted other ones, and they clump together in big clouds of gas called nebulae. And in the picture on this slide, you can see a nebula that's been observed today. There are still many, many nebula in the universe. At some point, the hydrogen became so hot that its nuclei were moving really, really fast, and normally 2 protons, that's the nuclei of hydrogen, would repel each other, but if they're moving really, really fast, they can overcome the repulsion and they can join together or fuse together. And when 2 protons fuse together, they form helium, because helium's got 2 protons in its nucleus. And when hydrogen starts fusing into helium, light and heat energy are given off. It's a nuclear reaction. And at that very point, a star has been born and begins to shine. The picture shows the sun. The sun is a typical star which emits light and heat energy by converting hydrogen into helium. It's basically a big nuclear fusion reactor. This joining together of hydrogen into helium is called nuclear fusion. Nuclear notation. So that physicists and other scientists can identify each element very clearly, we use nuclear notation. For example, in this diagram, the H is the element symbol. That's the one you'd see in the periodic table. This particular one is an H for hydrogen. The number at the bottom is called the atomic number. That's the number of protons in the nucleus. And it's this atomic number that determines the element. The number at the top is called the mass number. It's the number of protons and neutrons together in the nucleus. In the nuclear rotation shown, we have the element hydrogen, one proton in the nucleus, and there are no neutrons in the nucleus, so the mass number is 1, that's just the proton. And there's a little picture of it on the right. That's a hydrogen atom. Notice that in the nuclear notation we don't make any mention of electrons, even if they're there. We only deal with what's in the nucleus. And electrons are not in the nucleus, they're outside. Here's another example. Before I show you, try and identify what this is. Well, what element is it? What's its atomic number? And what's its mass number, shown in red? And what particles are in its nucleus, do you think? Well, the symbol is H, so it must be hydrogen. If it's hydrogen, it must have one proton in the nucleus, so the atomic number is 1. But what's different here is that the mass number is 2. That means there are 2 particles in the nucleus. Now, if it's hydrogen, it must have only one proton, so there must be a neutron in the nucleus as well. And when you have a particle which has the same number of protons in its nucleus as another particle, but a different number of neutrons, that's called an isotope. So what we have here is an isotope of hydrogen called deuterium. And the diagram shows there it's very similar to ordinary hydrogen, except it's got the neutron in the nucleus as well as the proton. This table shows a number of different elements and some isotopes of these elements. Remember, 2 isotopes of an element have the same atomic number, that's number of protons in the nucleus, but a different mass number. And I'll just identify some of the isotopes. You can see nitrogen 14, if you can find that. Look at its nuclear symbol, N, atomic number 7, mass number 14. And then compare it with the one below, that's nitrogen 15. Still got atomic number 7, it has to if it's nitrogen, but it's got an extra neutron in the nucleus. It's got 15 of mass number. So those are 2 isotopes of nitrogen. Nitrogen 14 is the much more common one. And similarly, oxygen 15 and 16 are isotopes as well. Well, scholars, I hope you enjoyed that. That brings us to the end of the Cosmology course. Thank you for watching.